All right, let's get started. So I'm going to try to start each time by introducing some new tools, and sometimes it'll be quick and simple, and sometimes it'll take a while. But I'm going to try to start by each lecture by introducing some new tool to you. There are tons of them, and so I've had to sort of cull through them and figure out which ones I think are not necessarily the most important, but maybe the most accessible and the ones that you'll probably end up using the most. So in order to use a lot of these, you're going to need to have some packages installed. And the most important one is probably binutils, but you can get that by running that command at the bottom. Apt install build essential, which you should absolutely have. And when I did this under the Windows subsystem for Linux running Ubuntu, I also had to install GDB, which is the GNU debugger that we'll cover in a later class. And so if you do that, hopefully that will get you mostly up to speed. There are more things you'll need, but we will bring those in as we go through the class. I've been running a lot of stuff in Windows subsystem for Linux. It looks like it's going to work just fine, at least for me. Your mileage may vary. So objdump is a tool you'll use a lot over the course of this class. An object file is just a computer file that contains machine code, data, resources, whatever a program needs to run. And it can contain links to other programs. A dynamically linked executable doesn't contain those dynamically linked libraries. They're dynamic. It just contains information that says, I need these libraries. And then it's the job of the dynamic linker to solve that problem and connect them all up. We'll talk more about linking than you probably ever want to hear in a future class. But objdump lets you explore what's actually in these files. And there's quite a lot in there. It's not just machine code. There's metadata that can be information about when it was compiled, who compiled it, the compiler that was used. There's going to be tons of information present in there depending upon the tools that people use, and you can explore that with objdump. Not everything in the object file gets loaded into memory. Some things are just there as annotations of information. So you should play with objdump a little bit and get a little bit familiar with it. Some useful options. -H is your friend, and it's -H because -lowercase h tells you the section headers in the file, and that may not be what you want. There's a special flag -W. Objdump can display a lot of tables that are present in a file. Those tables can have a lot of fields. And as a result, what objdump does is it wraps it. So you see here, it's got 2 lines for this one entry.txt and then 2 lines for this entry.data. If you use the -W and you have a wide enough screen, you can make the table look a lot nicer and make a wide table. It's good for wide consoles. It's less good for slides. Sorry. All right. So with that out of the way, let's talk a little bit about computer architecture. So I just want to get you up to speed on what we need for the class. You've probably seen all of this. This is going to be a review, but in the past, I haven't done that, and it's turned out to be something that was needed by some of the students. So here we go. Memory instructions and the fetch, decode, execute cycle. So here's a very basic view of the architecture. It's incredibly basic. In fact, it's so basic that it's wrong, but it's a useful model. There's a processor somewhere. This one's an i7-8700, which used to be the processor in the computer I'm using right now, but I've since upgraded it. So the processor sits there. There's memory. There used to be a separate I/O chip on the north bridge. Now it's really part of the processor. But this is your basic conceptual model. I've got input-output that talks to various devices, a processor that executes instructions, and memory that holds instructions and data. And I talk to these things using two buses, the address bus and a set of control lines for it that determine who gets to read or write to that bus at any given time, and a data bus where information is placed on the bus and anyone who's on the data bus can read that information. This is all mediated by the system clock. The system clock is not a clock that tells you what time it is. It's just an oscillator that switches between a high state and the low state. And so typically you'll see diagrams that show how memory access or other things happen with respect to the systematic clock. So on the rising edge, perhaps the processor takes control of the address bus, latches an address on the bus. On the falling edge, the memory controller reads that, looks at the memory, latches in the value in memory. On the next rising edge, the processor can then read it. So things like that. We're not going to get too deeply into all of this. It's just good to have a model in your brain of what's happening, because you have to think about this a lot more when you're thinking about assembly, and especially when you're thinking about things like malicious assembly. What's really going on? I said that it was so simple, it was in fact a lie, and that's kind of true. However complex you think the computer is, it's certainly more complex than you think. So microarchitectures are basically how you lay out the components of the processor on the die, and they themselves are fairly complex beasts. Different parts of it have to talk to each other. I have to get information from a register to, let's say, an arithmetic unit to do some work, or I have to get information from a register and stage it for writing to one of the caches, or maybe stage it for going out into memory. All these little pieces have to coordinate and talk to each other. Lots of things, in fact, a shocking number of things are happening at the same time. And so you have a very high degree of concurrency. Because you have a high degree of concurrency, you may wonder, how does the chip maintain consistency? It turns out it kind of doesn't. If you're familiar with sort of the modern database paradigm of eventual consistency, the processor is kind of doing that. It's not in nice lockstep, making sure that every write and every read happens in the order they're shown. It's really trying to get through a schedule of work as quickly as it can and do as much of that in parallel as it can. And as we'll see, occasionally that can trip it up. So if the processor is talking to the memory over some address bus and data bus, how is it talking to the other parts? How is the processor talking to itself? It turns out it's using its own bus internal to it. In the early days, it was a fairly simple on-processor bus. You could visibly see it if you looked at the die. Now, because these things are much more complicated, you have to invent other ways of dealing with it. Intel, for a while, used something called a ring bus that you can read about down here on these links. And now it uses something called the mesh interconnect. AMD uses something called its infinity fabric. So if all this sounds like they're fighting Thanos, they kind of are, because all of this is to manage this barely controlled chaos of the processor trying to execute all of these instructions. You can read about infinity fabric here if you care. This is an aside. Whenever you see this aside up here, that means I think it might be interesting to you, but I'm certainly not going to test you on this or expect you to know all of this. You can feel free to ignore this if you want to. I just think it's interesting. You can read about the mesh interconnect, the ring bus, and the system agent on the older Sandy Bridge architecture. And you can also read about how, again, complexity, when these systems get very, very complex, many things are happening at the same time. Sometimes there's a window for a vulnerability, and in fact there is. This is a little story about exploiting the ring bus. Fun stuff. If you want to understand how a processor actually really honest to God works. There's a really great series of YouTube videos where this fellow builds an 8-bit computer from scratch on breadboard and explains in way more detail than you may want how all of the pieces work. You can order all the little pieces and build it yourself. It's really, I think, pretty neat. And so if you're wondering exactly how a bus works on a computer and you'd like to know that, this will take you through that. If you want to know how to add numbers and how registers work, this will walk you through all of that. And it's pretty fun. But again, it's in the slides, so you can feel free to ignore it. Let's go back to our little model of the world. We've thrown the I/O away because really I/O looks like memory. It looks like addresses in memory. So here's our new model. We have a CPU. We have the address bus and its control lines, whether we want to read or write. And we have a data bus. And the CPU, you see, is controlling the address bus. And both the CPU and memory can read and write to the data bus. So what's in memory? Well, memory looks like an associative array, right? You've got memory addresses here, and then you have chunks of memory over here. And it's really chunks. Byte addressable memory is not really a thing. You have the illusion of byte addressable memory, but it would be incredibly inefficient to move single bytes in and out of memory. It would be borderline insane to do that because accessing memory takes a long time. And when you want to access memory, nobody else really gets to access memory. So you're freezing out other cores and other threads, and we don't want that. So really, memory is moved around in pages. And that's great because that also means you need fewer address lines. If you notice, this one just uses little 16-byte chunks. And so this last digit is always, this last nibble is always 0. And so we need fewer address lines. And that's how we get away with not having a ridiculous number of pins on the processor to connect to memory. Okay. So there's addresses and there's data and instructions over here. And they're stored together. This is called the von Neumann architecture, where I can interpret a byte, like let's say this, I think there's a 20 right here. That could be a space in a string. It could be the value 32, because 20 hex is 32. It could be part of an instruction, it could be whatever. And I can interpret it however it makes sense to me. It's not the only architecture. There is the Harvard architecture, which really tries to divide the world into instruction memory and data memory. And it shows up in some processors. Notably, ARM has a hybrid version of the Harvard architecture. Does that mean I can't treat data as instructions and instructions as data? No. Again, it's hybrid. Everything, nothing is pure, right? The x86 has some aspects of the Harvard architecture in it. It has the notion of earlier versions had a notion of a data segment, et cetera, and then there's some controls over how you can access different parts of memory, whether it's marked executable or not. And the ARM has some aspects of the von Neumann architecture in it as well. Nothing is nice and pure. So the processor operates in a fetch, decode, execute cycle. The first thing that it's going to do is look at the current instruction pointer and go ahead and fetch an instruction from that address in memory. So it gets the next instruction out of memory. Sorry about that. It gets the next instruction out of memory. Once it has that, its next job is to decode that instruction. And these two steps are a little harder than you might think they are. We'll walk through an example here in a moment to illustrate that. So we take the instruction we get out of memory, we convert it into a schedule of micro operations. Things may have to go in registers, they may have to go to memory, things may have to be added or multiplied. That requires use of an ALU. This all requires scheduling resources on the processor. And so you wind up with this, with a fairly intricate schedule, even for instructions that may seem pretty simple. So you wind up with a schedule of micro operations. And in fact, on a lot of modern processors, you wind up with a lower level version of the machine code that's usually running on a an embedded RISC processor to execute the instructions for the higher level processor. It's all turtles all the way down. Once we've decoded it and we have a schedule of operations, the next task is to execute that schedule of operations. So we do the work. And once we've done the work, part of that work is updating the instruction pointer. It may just move to the next linear instruction in memory, or it might be modified by a jump or some other instruction. And then we go back to fetch the next one, and we keep on going around this loop forever. The processor just keeps doing this forever for every core. And in fact, for multiple pipelines simultaneously, it's trying to do this sequence of operations. So that's how I would explain it. An important piece of this is the instruction pointer. Sometimes it's called the program counter. And so you'll see PC used and you'll think, is that personal computer? No, it can be program counter as well. It's always a good idea to overload acronyms with multiple meanings. So the program counter is a special register. A register is named storage in the processor that holds an address of the next instruction to execute. So the address, this is an important point, the address that's in the instruction pointer at the start of the fetch, decode, execute cycle is the address used for the fetch. Once we've decoded the instruction, part of that tells us where the next instruction is likely to occur, right? And so we update the instruction pointer to point to the next instruction before we execute the schedule. So the way that you should put in your head is the instruction pointer always points to the next instruction. If you think about it that way, you'll be in good shape. Instructions can modify the instruction pointer during their execution, and many of them do. The AMD 64 microarchitecture, that's the one we're using, names this register RIP. No other register is the instruction pointer. There is an EIP, there is an IP. They are not the instruction pointer. They have too few bits in them to be the instruction pointer. Only the 64-bit RIP register is the instruction pointer. And maybe it's worth mentioning at this time, that says AMD 64. You may be wondering about Intel. Well, many years back, when we were in the 32-bit world, people thought, hey, it'd be great to expand the address bus to 64 bits, have 64-bit processors. Intel created a 64-bit microarchitecture. And AMD created a 64-bit microarchitecture. Intel said this is a perfect opportunity to completely redesign the chip's architecture. And they created a really nice 64-bit architecture that looked very little like the old x86 architecture. AMD just said, let's add more bits, and made a bit extended version of the 32-bit architecture. So programmers were already very familiar with that. It was easy to port tools to it. It was easy to make compilers work for it. And so Intel has end-of-lifed the Intel 64 architecture, and AMD has really won out. So everything is now AMD 64. So if you're wondering why it's AMD 64, that's why. So even the Intel chips are using the AMD 64 architecture. All right. If you want to have someone on YouTube would explain the fetch, decode, execute cycle by repeatedly snapping his fingers with cool graphics, here's the video for you. Feel free to watch that in your spare time. All right, so let's think about interpreting an instruction. So let's say we want to go to memory and fetch an instruction and then decode it and then run that instruction. What does that look like in fine details? So here's our CPU, here's our memory. We want to fetch an instruction, so we go to the instruction pointer, RIP, and we have a 64-bit address in it. And here it is right here. We put that on the address bus. We set the read line. We want to read from the address bus. On the next clock cycle, the controller in our memory reads that. It goes and looks up the correct line of memory and identifies that here are the bytes at that location, and it puts them on the data bus. And then on the next clock cycle, the CPU can read this, and we're in good shape. So it takes a long time to read from memory. It doesn't exactly work that way. In fact, it can take hundreds of microseconds to read from memory for a variety of reasons. Mainly scheduling on the CPU, scheduling the memory read, because again, multiple cores are trying to do things. You have cache in the way. Lots of complexity is happening here, but this is a good conceptual model. I go to an address in memory and I get the bytes out of that address in memory, and I wind up with these 16 bytes. What do they tell us? So here are the 16 bytes written in hexadecimal. If you don't remember hexadecimal, this is a good time to make a note to yourself to go back and review it. Each 2 nibbles, right? A nibble is a single digit consisting of 4 bits. Each 2 make up 1 byte. So this is a single byte. The byte is 4C, so that's 4 times 16 plus C, right? A is 10, B is 11, so C is 12. So it's 4 times 16 plus 12, some value from 0 to 255. Right, 48 plus 12, which is 60. So there you go. We retrieve 16 bytes, and what do we do with them? Well, it turns out, hexadecimal. It turns out that in this case, the first 8 bytes of this make up a single instruction. Okay, so this is one instruction. An instruction can be from 1 to 15 bytes in length. And so typically the processor is filling its little internal pipelines with 15 bytes and doing it in single byte offsets and then trying to get as much work done as possible. But we can ignore that for now. We figure out that this is 8 bytes in length. Okay. And what's in that little instruction, right? So let's stop for a minute and say one more thing. Everything we're talking about now, just to emphasize, it's all lies. There's a cache controller. The cache controller on the x86 processor is Turing complete. The thing that fetches memory is Turing complete. It's just the way things go in the world of processors. Memory fetching is typically done in terms of pages, and that's mostly true. So that's one thing we can think that's mostly true. The processor talks to the cache controller. The cache controller talks to a memory subsystem, communicates on a bus. The DRAM controller is then responsible for trying to satisfy all the requests that it's getting. It'll take a lot of clock cycles to do it. And because it takes so long, the processor is trying to cheat. It tries to say, I don't know what these 8 bytes do, but I bet the next instruction starts right here. And it might not. And it may not even know it's 8 bytes yet. It may have yet to figure that out, in which case it may say, well, maybe it starts here, maybe it starts here, maybe it starts here. And in fact, it's simultaneously trying to interpret all of those instructions and perform execution of them. This is called speculative execution. And there's just a lot going on. It says multiple levels of cache. And so there are caches you haven't heard of. There are write-back caches that store information before it gets written back. And if the processor determines that it doesn't need to write a value back that you've told it to write, it will just never do it. And there are ways in which that can happen and yield very surprising results, especially when you have concurrent code. There's some bugs and even some exploits that have popped up from that kind of thing. All right, so enough about that. We don't need to get too deeply into the weeds on all of this. The important point here is that modern processors are always trying to load, interpret, and execute multiple instructions at the same time. So they're in all stages of the fetch, decode, execute cycle all the time. And they're trying to make various guesses. They do branch prediction. They do all sorts of different kinds of speculative execution. And that means on a processor like the x86 that you have to make some guesses about things, and you may be doing a lot of work that you end up not needing. And if that means the whole thing runs faster, that can be fine, right? Because all you care about is, at the end, the throughput of the processor. Maybe most of the work that that a processor is doing, most of it is getting thrown away just because it's doing so much various stuff. All right. If you want to know how that can turn into a vulnerability, because it absolutely can, there's a video here that talks about the Spectre quote unquote bug that uses the fact that the computer is doing real work as an exploit. The trick here is the processor does this speculative work, decides it doesn't need it, and throws it away. And that's all well and good. And you may think, well, there's no exploit there. But the work the processor does can have persistent effects, right? In particular, for Spectre, it can require that a page be fetched from memory. And then later on, we can detect that a particular page is loaded, and the only way it could have been loaded is if the speculative system caused that page to load, and that way we can communicate information back to ourselves from the speculative execution side. I know it sounds crazy, but again, this is a well-known attack, and if you're curious about it, go watch the video, and it'll be explained much better than I can. Paul will explain it much better than I can explain it. A key point of this, something that you should, this is not an aside, this is something you should know. A key point of all this is that all of these things we're talking about are abstractions. A machine level instruction can specify some work to do, but the processor is free to choose any method to do that work, as long as it has the same effect as what that work requires. So it can choose any method it wants to do. And in particular, the processor can do work out of order. It can do different but equivalent work. It can do extra work that we didn't ask it to do. And in fact, it's always doing extra work we didn't ask it to do. As long as the overall effect is the same, the processor is free to do anything. Okay, right? It's the goal here is for the end result to be what we want, and the processor is trying to satisfy that while also trying to do it in this as blindingly fast a way as possible. Whenever the processor changes the work schedule, you have the potential for a side channel vulnerability. And modern processors are always changing the work schedule. So I expect we'll get to see more of this kind of thing as time goes on. All right, enough of that. Let's go back to our 8 bytes. It's quite a long little detour, but I think it's worth mentioning. Back to our 8 bytes. So we fetched the bytes. The next step in the cycle is to decode them, to say, what do these 8 bytes tell the processor to do? Well, the first thing they say is go to the register file inside the processor and go to the register RCX. So RCX is a 64-bit register in the processor. Register is just a piece of storage in the processor with a name. And it holds, in this case, a 64-bit value represented here by probably not quite enough hex digits, but there it is, hex 13. Grab that and multiply it by 8. Okay. Take the result of that and add that to the contents of the internal register RSI. All right, so there it is. It's got this value in it. We're taking this times 8, adding it to this. And add 512 to the result of this combination. And when you do all that work, you get this. And then go out to that address and fetch some bytes at that address. These are the bytes that are at that address. We want to obtain 8 bytes that are at that address. 8 bytes is 64 bits. And these are the 8 bytes that are at that address. Add the 8 bytes obtained to the contents of the internal register R8. So we take this value, we add this to it, and we end up with this value. There you go. 8 bytes. 1, 2, 3, 4, 5, 6, 7, 8. So it's a lot to do, but we're almost done. Then set some flags. So there's a special register in the processor that holds what are called condition flags. And these tell you something about the result of the last operation. Some ones you'll look at quite a bit. The carry flag, CF, tells you usually if something is overflowed, but it can be used for other reasons. There's an overflow flag, specifically used for math. There is, what's another good one? The 0 flag tells you if the last instruction resulted in 0 for most instructions. The sign flag tells you if it was negative. And so the result of all this turned out to be this number. We didn't have a carry or an overflow. It's positive. It's not 0. So we've set them appropriately. So there's our work schedule. This is the set of things the processor now needs to do in order to execute this instruction. One more thing. We're almost ready to execute the instructions, but before we do that, we now know that the instruction is 8 bytes long. Once we've gone through the first round of interpreting, we know it's 8 bytes. And so we need to update the instruction pointer. And that's, in fact, the first thing we do before this schedule happens. So we update it, in this case, by adding 8. So we go from this value to this value, and it'll n turns into 8. And now we're ready to do the schedule of work. So when this actually runs, the instruction pointer is always pointing at the next instruction to execute. And that's a good way to do it. That means if this is a jump, we will load a new value into RIP and go back to fetch. If it's not, we just plow ahead because it's already been updated. We run the sequence of operations. We finish the execute piece of our fetch, decode, execute cycle, and we're ready to go back to fetch. So that was probably a lot. Let's talk about how assembly helps. So here's our 8 bytes of machine code. We call it machine code. And here is the corresponding assembly language. So this guy and this guy are, correspond with one another. And this has some of the stuff we saw. It's got R8 explicitly mentioned, RSI, RCX, there's that 8, that 512. So a lot of the pieces we saw up here show up down here. And it's hard to see them in this, right? It's really hard. You can squint really hard, but it's hard to see them. I can find the 512. It's right here. It's these last four bytes. But the rest of it, right? There's a SIB byte. There's a mod RM byte. You don't care about this stuff. You really don't want to ever try to hand assemble or hand decode machine code. There's lots of libraries that will do that for you. Go use one of them. All right, it's fraught. So this certainly looks better, and there are some specific reasons. One is the registers have names. So it's R8 and RSI and RCX. That's great. Another one is it's got a mnemonic. It tells me that I want to add something. In this case, something that comes out of memory. And all this work we did with grabbing these registers and adding them and doing stuff to them, that's computing an address. So I'm going to go to that address, get the contents of memory of that address, and then add it into R8. That's much better. That's much cleaner. So when I put this through an assembler, like NASM, which we'll be using, I should get out something similar to this. What I actually get out weirdly depends on the specific assembler I use. It's a fun world. And I might use a disassembler, right? I don't want to look at this. I want to look at this stuff down here. So I'll use a disassembler, which will read these bytes and produce something that looks like this. And that'll be great. And I've been pretty cagey about how this and how these two things relate to one another because they're not one-to-one. Would be great if they were, I guess, but they're not. There's some wiggle room when I give an assembler this kind of thing. There's some wiggle room as to what it actually writes out into the machine code. And when a disassembler reads machine code, there's a little bit of wiggle room in what it writes out as assembly. It's not perfectly one-to-one. In this case, it might actually be. There might only be one way of interpreting this and interpreting this. But for many other instructions, and we'll see that later on in the class, there is some potential variation in what it can do. All right, so what can these instructions do? Well, an instruction is fairly limited. It can read the processor state and it can modify it. It can read from memory and write to memory, and that's kind of it. That's pretty much all an instruction can do. They can modify the instruction pointer. That's a register inside the processor, so it's processor state. This slide points out they can be up to 15 bytes in length. Because of prefix bytes, you could theoretically construct an instruction that's longer, but the pipelines only take 15 bytes. So what we'll do is it will cause a processor exception if you do that. There are many instructions you can try to execute that will cause a processor exception. So the processor state is the registers like RAX and RBX and RSI and RIP and all the various registers. The flags like the zero flag, the carry flag, the sign flag, the overflow flag, all of those. There are operating modes for the processor. That won't matter much for this class. At some point, there'll be an aside where I talk about protected mode versus real mode. There actually are a few other modes as well, but those are the two big ones. The processor always starts up in real mode and then it switches to protected mode. Protected mode is just the mode that gives you memory protection, which you need for basic security. And there's DRAM, and the DRAM is accessed by the L1, L2, L3 cache and some other pieces in there as well. And an assembly instruction can, again, read and write processor state, read and write memory. That's really all it can do. All right, that's our quick journey through that. Let's talk a little bit about how control flow works in assembly, and we'll look at a few assembly instructions along the way. So most assembly instructions are like most instructions in any programming language. They do something, and then they fall through to the next instruction in sequence. We call that linear. So a straight line instruction typically transforms the processor state and then just plows ahead to the next instruction. And they usually set condition flags. They don't always, but a lot of them will set condition flags. In fact, there are many instructions that explicitly don't set condition flags. I'll try to call some of those out so as not to disrupt the results of a previous computation. So in this case, we have an instruction that says add EAX EDX. So we're going to add the contents of these two registers together, and we're going to store the result in EAX. And in machine code, that looks like the bytes 01, D0. Nice and short, 2 bytes. So where is EIP pointing right now as this instruction executes? Well, it's not pointing here, right? This is the instruction that's executing at this address, but EIP doesn't point here. It points to 02, 03, 04. It's pointing to the next instruction down here at 1204. And we can build that out. Starting address is 1202. We add the 2 bytes for the instructions. And right now, EIP has 1204 because it thinks that's likely to be the next instruction to execute. And it probably will be. Branching instructions typically don't transform the processor state, although there are a couple that do. But for the most part, when you see a branch, and it's not going to modify the processor state. An unconditional branch like jump, it's not going to modify anything except EIP, or sorry, RIP. Too many things in my head. Too many E's on the screen. So a jump to 1215 is going to load this value into RIP. So the next time we go to the fetch, we're going to load from 1215 instead of what we normally would have, right? 11EF, 11FO, 11F1. We're not going to load from 11F1. We're going to overwrite that value with 1215 and load from there. Okay, that's all an unconditional branch does. Loads a new value into RIP. Various ways to do it. We'll talk about some of those. So at the start, the instruction pointer is in fact pointing to 11F1. It's not the next instruction. It's a relative jump. You may wonder why we see 1215 here, but over here we don't see anything resembling 1215. This is a hex address, but there's nothing over here that mentions it. What's actually happening is this is a relative jump. So it's saying take the contents of RIP, which remember points to 11F1, and add hex 24 to it. We do that math, we get 1215. And there he is. So there you go. The disassembler has helpfully figured that out for us. All right. So after that, the instruction pointer holds this. And now when this instruction begins to execute, it's going to hold 1215, 16, 17, 18. It's going to hold 1218. Right. Branching instructions typically do not transform the processor state, but instead examine it and modify the instruction pointer only. And conveniently, they all start with J. That's pretty nice, right? They all start with J, except this is x86, so there's always an exception. We'll talk about the exception later. Yes, there is an exception that modifies more processor state and doesn't start with J. It's a fun world. But just remember that whenever you see an instruction that starts with J, that is a jump. If it's JMP, it's an unconditional jump. If it's J and something else, it's a conditional jump. It's conditional. We would call it a branch, conditional branch. So this says something about jump if equal to this address. And so we would go and look at the condition flags to figure out whether or not to make that jump. At the start, the instruction pointer, 11F9, points here. 11FA is here, and 11FB is the next instruction. Remember, hexadecimal. So right now, as we're executing this instruction and figuring what it does, EIP holds 11FB. The JE instruction looks at the 0 flag, and if it is set, then the jump is taken. So jump if equal actually asks whether the 0 flag is set. And if it's set, it takes that jump. So if the 0 flag is set, it will load this value, actually add this offset into RIP. Right? The new address will be the old RIP plus the offset right here, which gives us the new value for it. If it's not set, then we don't modify RIP at all. And it already points to the next instruction, so we just plow right ahead. So that's what it ends up looking like. It ends up saying, you know, if the 0 flag is set, go down here. If it's not, don't modify RIP, which already points here, and we just would fetch from this next, and we just plow ahead. Okay. We're going to look a little bit at all the different conditional jump instructions. Many of them end up being synonyms. You may wonder why I keep saying jump if equal checks the 0 flag. That's because jump if 0, JZ, and jump if equal, JE, are synonyms. These two mnemonics are the same instruction. And so this is an example of some of that wiggle room, right? If I write JE or I write JZ, the assembler is going to give me the same opcode. And the disassembler might show me JZ or it might show me JE. Just depends how it's feeling that day and how they coded it. So assembly language isn't going to have the control flow primitives that you're used to. It's not going to have nice looping structures. It does have, there is a loop structure in x86 we'll cover later, but it's not going to have nice if then else's and all that. You have to build them out of something more primitive. And that makes sense, right? A higher level language is a higher level language because it gives you these higher level abstractions to write your code. Assembly doesn't do that. It's not really concerned with it. So I've shown you a couple instructions, adds and some branches. You may wonder how many of them are there, right? I want to learn them all. I want to learn all the instructions. How many can there be? And it turns out there are a lot. Exactly how many there are, we don't know. This is one of those fun moments. There have been attempts to measure them, which we'll talk about. How can we not know, right? There's documentation for the processor. Well, yeah, we'll get to that. So different ways of counting them based on the documentation give you different results. There are two major dialects, and we'll talk about this in a later class too, AT&T and Intel. If we count the mnemonics in the AT&T dialect, there are about 1,279. If we count the mnemonics in the Intel dialect, there are 981. So these are different ways of expressing the assembly, and there are different numbers here, which is mildly disturbing. If we consider mnemonics and operand types, right, adding a 32-bit register and a 32-bit immediate value would be 1, for example. Then the number goes up to almost 4,000. If we just consider operand width, it drops down to around 2,000. But what about just every instruction? These are all sort of hedging and based on the documentation. What about every valid bit sequence? We don't know. But maybe there was a way to find out. So Chris Domas took it upon himself to go and try to find out. And he started a little project called the Sand Sifter Project, which you can read about at this link right here. It's a GitHub link. So in fact, you can go get the code and do this yourself. And what he found out is pretty interesting. x86 chips are packed full of secret instructions and hardware bugs. He used some really neat processes. You should maybe spend some time reading this if you are interested in it, to go and figure out what's in there. He found hardware glitches, unknown machine instructions that just popped up, and lots and lots and lots and lots of bugs and flaws. So it was pretty interesting. It's a fun little project to read about. He basically, if you're familiar with the notion of fuzzing, he fuzzed the processor in order to plow through all the different, the quintillion different possible instructions. He fuzzed the processor to get some of that, and you can go and download the code and do it yourself if you'd like. And there's you may want to have him talk about it. I'm giving you my view of it. His lecture from Black Hat is linked in the slides. You can feel free to have a look at that. It's really, I think, interesting, fun stuff that tells you a lot more about how the processor actually operates. Because again, these things are hideously complex. All right. So the point is there's a lot. And I do not expect you to be an expert on x86 assembly language. I know a couple of people who I would consider experts on x86 assembly. And they will happily tell you they don't know what's going on some of the time, that their knowledge is incomplete, and sometimes it ends up being wrong. You really just need to know the basics, and that's what we'll try to do. New features are added all the time. People who write compilers have to try to fight to keep up with this, because sometimes the new features are added to support a particular compiler or a particular change in the architecture, and then you have to go back and patch it. LLVM does a really good job of documenting their whole process and what's going on. Because it's newer than GCC, you can sort of find a lot more of the historical data for it. And it doesn't mean it's better, it's just newer. And so they've done a much better job of putting documentation out there. And as an example, 512-bit registers were added. And so if you're a compiler writer, you want to be able to take advantage of 512-bit registers. And this requires some planning. So when they add the new registers, it doesn't just mean, hey, there's some new registers and there's some new names that go in your assembly. Typically, they come with additional instructions. And if you glance around the slide here, and I know it's kind of an eye chart, sorry about that. The URL to the whole thing is over here if you want to see it in glorious detail. If you glance around this, you'll see down here 651 instructions and over 4,000 intrinsics. So even adding a few new registers turns out to be a fairly complex thing. And they're getting there, right? They're getting there. They're really excited because 30% of the instructions are now implemented, right? It takes a while to get all this stuff built in. The idea being we want to be able to take code that looks like this and turn it into code that uses these vector registers, these 512-bit registers. On a 512-bit register, many ways I can think about it, but one really nice one is as a vector of lots of other values. So, right, how many 32-bit values can I pack into that register? Well, a lot. And then I can do work with them by adding vectors, adding the registers together, and doing other stuff. And that can speed things up a lot. All right. Whew. The instruction set architecture changes a bit with each new processor. It changes a bit, changes a lot actually with each different processor family and with each product line. But Intel and others try to maintain backward compatibility. They try to be sure that the old code you had will still run. That's true in ARM as well. So the 32-bit ARM had two modes of operation, thumb mode, which was basically a 16-bit mode, and then the 32-bit mode. When 64 bits took over the world, ARM added a 64-bit mode and kept the old 32-bit mode and disposed of thumb. So sometimes you cut some stuff, and in fact, the AMD 64 does cut some stuff. It changes the way certain things work. But for the most part, it's backward compatible with the 32-bit stuff. Not perfectly, but it's there. And so the stuff that you know about the processor will carry you forward to new ones as it goes forward. But there will be lots of changes. All right. So let's take a 5-minute break. And when we come back, we will talk a little bit about how our programs actually run on the machine, what that looks like. My watch shows 9:57, so let's say 10:02. So get up, stretch your legs, get a drink, and we'll meet back here in about 5 minutes. Teaching assembly is always a bit challenging because it turns out that it's very difficult to tell you much about it until I told you a lot about it. So it's kind of a chicken and egg problem. And in the past, there have been many cases where only later on have I realized that some students had a bad mental model of how the processor was operating, and so thus all the architecture stuff. I hope it was all review and nothing was really new in there except maybe some of the asides. But if it wasn't, then that's, I guess it's worth doing. All right, so let's talk about a little bit about how programs run, and they can run with or without the C runtime. And in a later lecture, we'll actually take a look at how the C runtime gets in there. And that's great because that's also a good source for injecting maliciousness. There is a standard for C, and I recommend you grab it and read it cover to cover, because nothing is more gripping and exciting than reading a language standard. It's a great way to lose your will to live, I think. So anyway, if you want to see it, it's there. You probably don't care about most of it. It does tell you a little bit about how programs start and end, and that can be helpful information. So program startup is covered in the standard. It says you got to have something called main, and it's fine for it to have 0 or 2 or other. And in fact, on Linux, the answer is other. You can write that and it's fine, or you can write argc and argv and that's fine, or you can write argc, argv, and envp for the environment pointer, and that's fine too. It's not part of the standard, it's just an extension that's there in Linux. Tells you a lot about how this stuff has to be laid out. These will contain pointers to strings, etc. 0 will be the program name, and this has to be the null character if the program name is not available, and so on. Lots of information. If you're building an operating system and you want to start a program through the C runtime, you need to know all this stuff. Otherwise, it just tells you a little bit about how the programs work. Programs can exit, they can return, or they can just hit the ending brace, which is an implicit exit 0. There you go. And pretty simple stuff. So that's the basics of what it says there. Here's some C code. Super complicated code. There's that envp I mentioned. This gives you access to the environment variables. If you want direct access to them, you can get it this way. And it writes out the string hello world and returns 0. There you go. Super complicated code. We can compile it. There's your GCC compile line. We can run it. It prints hello world and it returns, in fact, 0. Nothing new here. So when we actually run it, the operating system has to do a bunch of stuff. It has to figure out what the program is, right? It could be it's a straight up executable. In this case, it is. It might be a script. In this case, it's not. But it could have been. And so once it's figured that out, it has to then map the parts of this that it needs into memory. What parts have to get mapped? Well, this has some code. So code has to be mapped into a page in memory that is marked executable. Typically, it's marked not writable. Has some data. This data may get mapped into a page in memory that's not writable and not executable, or it might get, depending upon how things are done, it might be mapped into the same page as this code, which would be great for me if I'm a malicious person, because then I can put some stuff in the string and run it. But for the most part, we're trying to be good and disciplined in the world and keep our data and our code separate. And so these will get mapped into different areas of memory. Looks like they're all together here, but in reality, this will be mapped somewhere into a read-only data section. So then it has to load all that stuff into memory. It has to figure out the addresses of all of that stuff, right? Main is going to have an address. This string is going to have an address. These things will end up probably on a stack, and they'll all have an address on the stack. And all those addresses have to be figured out. So when it then runs, something has to know where to find put s. Maybe that's in a library. Something has to know where to find the string. And all those things have to be linked together. And that's the job of the linker. Many different kinds of linking. There's static linkage, where you just put everything you need in the file. The offsets are all defined by what's in the file. Memory locations may be static. You load that and run it. It's not optimal to do it that way, and we'll talk about how to not do it that way in a later class. And there's dynamic linkage, where maybe we don't know any of the stuff until runtime, and we have to figure it out when the program starts. Like, where's put s? Oh, I put it here. And so we fill in the address with it. We'll talk about how that works. There are data structures that get set up in C. There are thread pools that get allocated. There's memory that gets allocated and stuff like that. Once it's set everything up, once it's created a nice cozy environment, nice cozy, safe, secure environment for our program to run, it then transfers control to main, which runs, and eventually transfers control back to the C runtime, which is then responsible for deallocating thread pools and unwinding various stacks and doing other things and cleaning up memory and so on, and then returning control to the operating system. Okay. What's actually happening during all this? Well, we can run this little piece of code, hello world, with something called strace. Strace is a tool that lets us observe all of the system calls. Right? System calls are services provided by the operating system to do things like read and write, allocate memory, etc. And so we can see what's actually happening. So let's take a look. So we strace hello, and we get some output. You can reproduce this on your machine. It reproduces almost exactly under the Windows subsystem for Linux, which is great. So there we go, strace hello up there, and then there's a whole bunch of output. So let's look at some highlights. So exec VE, right? So we've at some point we forked the process, and now we're going to execute something. We're executing hello. There's our argument list. There's some stuff. 34 environment variables are present in there, and there you go. So we're executing it, and it returns 0. So that's great. So we've seen exec VE before. This is what the OS calls to begin execution of the program, and then some stuff happens. And that stuff is a lot of library information is read into memory. So you see up here the library preload list, the cache list. You don't want these things to be writable by average users, or it's a really bad day. So those get read in. That tells me where to find stuff. I then go ahead and get the standard C library, libc so6. I'm going to need that because I use puts. And so I need to get that mapped into memory, and those things get mapped in. So you can see stuff happening here to do that. See some mmap commands that will allocate and map memory for me. And so all this library information gets read in, a whole bunch of stuff happens. I adjust some memory limits. The break system call modifies where the program break is located. Mmap and break are in some ways different ways of manipulating memory. We tend to, modern stuff tends to rely more heavily on mmap. Older stuff, if you look at old 32-bit code, it's going to rely much more heavily on break. Just the way it is, right? Nothing ever goes away. We just add more layers. That's, in fact, what we do. And then finally, if there's time, your program runs. And so we've done all this stuff, set up this nice, cozy, secure, safe environment with all the resources the program needs, and then we run your code. And we have a write system call that writes to standard out, which is file descriptor 1, the string hello world with a new line, 13 bytes. It does that, and so it ends up in the mix right here because that's where it happens. And then the write call tells us how many bytes it wrote, which in this case was 13. And then we unwind the thread group and exit and terminate the program. So operating system is living up here, and down here it's running the whole time, doing stuff. And what we're seeing is the stuff that the C runtime does initially, and then finally, just to get your little program to run. So, right, the operating system sits around a process. And you could directly start your process from the OS. You don't need the C runtime technically to do anything. You don't even really need it to use the C libraries. And in fact, they have to be designed that way for obscure reasons that I want to go into. So the operating system can start your process. Your process can request resources from it, and the operating system can actually communicate information to your process. And then finally, your process will return control back to the OS. There you go. Unless you're building an operating system, in which case the whole thing is one big blue box, and it's going to be just horrible. All right. It can be a little tricky to build code in this environment, but not too bad. We will do that in this class. The other way to do it is to create a nice cheery wrapper around your code, which is a C runtime. I keep saying C runtime. Are there other runtimes? Yes, there are, right? I mean, there's Java's runtime. There's even stuff like Rust and other languages that target quote unquote bare metal provide a runtime that makes all this stuff work, that mediates your communication with the OS, right? If I'm in this world, I have to know a lot about the surrounding operating system. I have to know that it's Linux. I have to know how to operate inside that environment. In here, I might not have to know so much of that, right? My code might be much more portable. I want to write, so I use printf as opposed to trying to use the Linux write system call. And because I use printf, I can then substitute this with the appropriate C runtime on Windows and do the same code on Windows. And that's very nice. The C runtime handles a lot of work of this, and C compilers handle a lot of work of making your program ready to run in this environment. So let's take a look at some assembly in both cases. Here is some assembly you can stick this in a file, and you can assemble it, and you can run it, and it will in fact work just fine on Linux. It does not use the C runtime. It doesn't use any of the C libraries. It does everything all on its own lonesome. And so you can see up here at the top, it has a start. There's our start symbol. It's not main. There's no main anywhere in here because it's not using the C runtime. On Linux, the traditional start symbol is start, underscore start. And it's similar on most platforms. We are going to use a system call. So we put some values. We put 1 in EAX, 1 in EDI. We put a pointer to our message down here, hello assembly world. We put that in RSI. We get the length of the message, which we compute down here. And we'll talk about this later. So if you're not understanding all of this, don't panic. We get the length of the message. We put that in EDX. It turns out this is how you set up your arguments for a system call. And then we do a syscall. And the result of this instruction is to write this string out. We then put 60 in EAX, 0 in EDI, and do a syscall. And the result of that is we tell the operating system, I'm done. Please take me off of the scheduler and deallocate my memory. So after that, we can't do anything. There's a halt instruction that's sort of pro forma, but this syscall will never return because we get descheduled. There's some read-only data that lives down here, but that's it. Our program is nice and short and sweet and pretty simple. And it'll work. And if you want to know how to make it work, over here are the instructions to do it. And you should do it. You should grab this, throw it in a file, assemble it, and run it, and see what you get. Play with it a bit if you want to. Here's this basically the same code, but now we're going to use the C runtime. And so you see immediately one important difference is main. We have a main function here for the C runtime to go and call. It wants you to have a main function, and we provide it with one. You'll also notice there's this extern putS. We want to use something out of the C libraries, mainly putS, and we have to declare it, just like you would have to declare a function extern or something else in C. We do the same thing in assembly. So this says, I want to use putS. I don't know where it is. It's somebody else's job to figure that out for me. And that'll be the job of the linker. Then we do some stuff. This first stuff has to do with something called the calling convention, right? How do I get arguments to my assembly? How do I get return values back to the caller? Turns out that's not obvious, and there's any number of different ways to do it. We will use the AMD 64 calling convention, and that's how we'll interact. And this is sort of part of that calling convention. We put a pointer to the message in RDI. The register RDI holds the 64-bit address of message. We then do this call put s with respect to PLT. We'll talk about how that works later. We just call put s, put a 0 in EAX because that's what we're going to return. We pop this off the stack and we return. And you can do the same thing. You can assemble this and you'll use GCC to link it. It's a convenient way to get the C runtime built in and get the standard C library included. It'll do that by default. GCC assumes you want to build C code, and so it includes those things for you, even though, in fact, we've built some assembly. Right? Once you've assembled it, it's a .o file. And you can link all these .o files up however you want. Right? The system after that doesn't care. And it produces a 16K executable that prints hello C world. Our previous one made a just under 9K executable. So a lot of additional information has been packed in here. What is that? It's probably all this information to do with the standard C library and the C runtime. If we run without the C runtime, let's go back and strace our version without the C runtime. Here's what we get. Notice there's a slight difference, right? Here's the exec call, and then our program runs, and that's it. Right? All that stuff about setting up a thread pool and then deallocating the thread, all those various things, none of that happens here. Right? It's up to us to manage memory and everything else on the system. That means that we have to take responsibility for it, but it also means we have the ability to make whatever changes we want to make in that environment. And that can be very, very powerful. Right? In this case, our program does what it says and nothing else. Most programs you're going to encounter, even malware, even like nasty malware, are going to use the C runtime because, of course, they are. Because why wouldn't you, right? I mean, you're like, I'm going to hammer these nails in with my fist because it's harder to do it that way. No, you go get a hammer and use a hammer, right? Now, embedded programs, the C runtime itself, parts of the operating system, and plenty of malware I can think of don't use the C runtime. They want to cheat in various ways, and so they need to not do that. Right? They want to either be small enough to fit inside a payload and be unsuspecting, or they want to do things that are difficult to do when you have the C runtime sitting in there. So the point of this is you need to understand both ways of operating to be able to understand how these programs operate. All right, so if assembly language is going to be hard, and it is going to be hard, why are we looking at assembly? Why are we doing this? Assembly is hard and unintuitive, right? That's why we have high-level language. That's why C and Rust and Python, all these other languages exist, because it's just easier to write code. So why would I analyze a program in assembly language? And there are a variety of reasons. We might not have source code, right? Malware. It surprises me how often you can find the source code for malware out there. It's not zero, which is what I would have expected. It's not a lot. Occasionally you can. People sometimes will post their stuff. We found code for malware on Google Code. We found it in repositories. It's kind of surprising. Sometimes you do in fact have the source code for malware, but most of the time when you encounter a new piece of malware, you're not. You're gonna have to throw it in a disassembler and look at it. Legacy software, it's shocking to me how often organizations can't find their source code. They lose it, and then they have important intellectual property and trade secrets and other good stuff that only exists as compiled software. And that's mildly disturbing. IRS is a good example of an organization that has tons and tons of legacy software that is written only in assembly and is having to deal with that. Games, you might want to make some modifications to games that are out there so that you can see your adversaries through walls, so that you can pass through those walls, so you can magically turn clip and no clip on and off when you feel like it, without necessarily using cheats. And so the people who built the game aren't necessarily going to give you the source code, but you can dig through the game and find out what to do things. So there's lots of reasons you may want to work directly with the assembly. Another reason is there are in fact decompilers. Hexrays makes a decompiler. Ghidra has a decompiler in it. These are approximate at best, right? Take a small program, compile it, put it through one of these decompilers, and compile the result, and you'll get something completely different probably, all right? If it even compiles. It's very approximate. That's just the nature of trying to translate, right? When you translate languages, oftentimes you will try to use the appropriate idioms for the new language, and it's not always going to be exact. And then if you translate back, that's not going to be exact, right? This is how you get the game where you take a sentence and you put it through Google Translate 5 or 6 times and you get out nonsense, right? Same thing here, right? I compile, I decompile, I compile, I decompile. Pretty soon I have nonsense, just because it's the nature of the beast. Compilers are also approximate at best. We'll see an example of that in a few moments. Source code, you should think of that as strong advice, right? You're like, I would like you to add these 2 numbers. And the compiler will say, you know what? I might do that. I might get around to that. And it emits machine code. And then the processor has to think, well, I'll do that. Maybe I'll do that. Maybe I won't, right? Source code is strong advice. It's usually going to do, it's going to try to divine your intent and do what you want it to do, but it may not always do that. And so if you want to know what's actually going on the machine, you need to look at assembly, right? Compilers can, and they do, add, remove, and change the behavior from what's in the source. They do, for a number of reasons, most of them having to do with performance. So here's a program. Let's give an example of that. Here's a program. It's not a complete program. There's no main function, but that's okay. We can still compile it. We just use the -C switch to GCC, and that will compile but not link it. So we call it a little function delay. We have 2 characters, I and j. We set j to 0, and then we go into a while loop and we decrement it. And while we're decrementing it, we set I to 0 each time, and then we run this little loop and decrement it here. So it's 0. The first thing we do is decrement it. So now it's 255, which is not 0. So the while loop runs again, decrements it. Now it's 254, and so on until it gets down to 0. So this will run 256 times. The outer loop will also run 256 times. So the total time would be 256 times 256, right? That's 2 to the 8th times 2 to the 8th, which is 2 to the 16th, which is 65,536 times through this little loop. And there you go, little tiny delay function. You see there's a lot in the embedded world. So let's compile it, and then we'll disassemble it using our old friend objdump, which we talked about at the beginning. And if I say objdump-m intel, which I need to do in order to get the intel form, you can try it without that and see what you get, and a -d, it gives me this little disassembly. So here's my program. I compile it with the -c switch, GCC-c, delay.c, and then I look at the assembly I get. And again, I don't expect you to be able to read all this just yet. After the next couple classes, you'll be able to read this just fine. But you'll see that there's a J, and I've told you that J signals a jump. And so JNE to E, okay, that's great. That goes up here. JNE to 12, that goes up here. jump, that goes down here. It's sort of traditional to write when you're drawing little flow graphs in assembly to use solid lines for unconditional and dashed lines for conditional. And that's what we've done. So we plow into this, we jump down here to the bottom, we subtract 1 from something, we compare it to 0. If it's not equal to 0, we jump up here and we subtract 1 from something, compare it to 0. And if it's not equal, we jump up here and we start doing that. So this is the inner loop where we're decrementing, I think it was J. And this is the outer loop where we're decrementing I. So there you go, the loops show up. This weird jump down here is a fairly common thing you'll see in assembly, right? There's not a nice while loop structure. And so if you want to do the predicate first, you sort of have to jump down to the bottom of the loop where it's being tested. We can optimize it. If you put a dash capital O in here, that enables the optimizer. Now look at that. Now, over here, we had a bunch of stuff in memory. So here's some stuff in memory. This is all stuff being read and written to memory. That's all gone. And now we just have stuff happening in registers. And it's worth taking a moment to note why that can be important. Let's say I'm debugging this program and I want to know the value of I at some point. Well, in this world, that value lives in memory that I can go and inspect. And it should be consistent. In this world, that value lives somewhere, probably in a register, maybe in part of a register, and it's much more difficult for me to inspect at runtime. So that's why you typically you either compile with debugging or you compile with optimization. All right, the loops are still here. Here's the inner loop, super tight now. We just do a sub 1 and then a jump if not equal. It's pretty easy. Don't need to compare it to 0. We just know that f has to subtract, and I get 0. This will fail and I'll fall through. And then I subtract 1 from the other one, jump if not equal. That's the outer loop. Super tight code, very, very, very simple. Let's optimize. Can we optimize any further than this? Sure. We can throw a dash O2, which says, do full optimization on it. When we do that, the compiler says, okay, you don't need to do any of that. And so I won't do it. The compiler has determined that it doesn't need any of this and threw our code away. Why? Well, it doesn't return anything. It didn't take any arguments, right? So nothing is passed in or passed out. Nothing in here references a static variable or an external variable in the module. It doesn't call any external functions that would have a side effect. So therefore, this has no effect, and it throws it away. This is a common problem when you're writing embedded code. You need delay loops. Compilers love to throw away delay loops. It's a common problem when you're trying to write secure code. For example, someone's entered a password, and now you're going to overwrite that password in memory to be sure it can't be read. The compiler determines that your overwriting code is overwriting part of the stack that's going to be reclaimed. And so it throws away your security code. It's very common. Lots of security code is thrown away by optimization. Just one of the features the compiler provides. So in this case, we gave the compiler some advice, and it said, no, thank you. That's fine. We told it to optimize. It's really on us. So again, the compiler can do various things. If it had decided that changing the order of things here was better, it could have done that. It can do that sometimes because of pipelining. It may be better. It may help the process to keep its pipeline more full if it moves tests later in the code and moves other stuff up. A common optimization is to figure out, I need a memory reference here. That memory reference is going to take some time. And so while that's happening, I can do other instructions. And then when that result gets back, then I'll do the instruction that required the memory reference. And as long as I'm able to do things out of order in that way, I'm fine. There are some out of order execution bugs that have showed up in the past. dealing specifically with that one, filling the memory fetch slot. All right. So if you analyze source code, you're analyzing an approximation, right? Analyzing this code over here, this C source code, was much easier than analyzing the assembly, but this told us nothing about what the program did, right? The information we get from looking at this is useless because it's not what the program will do when we run it. Okay. Compilers insert code you didn't write. They really do. They change your code in a variety of fun ways. So if you want to know what your program's going to do, you need to try to figure out and get as close to the code that's actually going to run. I point out that, it's a scary sentence, even the output of a disassembler might not be true. We'll see that a little bit later on when we talk about tricks that malware authors use to avoid being disassembled. Assembly language is often about as close to the ground truth as you can reasonably get, right? You don't want to have to read machine code. Reading assembly is just much more reasonable, and it's a much closer version of what the machine is actually going to end up doing. High-level languages are abstractions, right? The code specifies some work, but the compiler is free to choose any method to accomplish that. And what is it trying to accomplish? It's trying to accomplish the thing that the compiler writers considered to be the important effects. Right? One of the things that they do is they run through your code, they try to figure out what they can throw away, and they throw that stuff away because nothing is going to be faster than code you don't execute, right? That's going to take 0 cycles. And so the more code they can put in that don't execute barrel, the happier the compiler writers are going to be because it's going to be faster. The compiler can specify work out of order, and it does. It can do different but equivalent work, and it does. It can do extra work, and trust me, they do. And it cannot do requested work. As long as the overall effect is the same, it's free to specify anything. And just like when we were talking about the processor, whenever the compiler can change the work schedule, you have the potential for a side channel vulnerability. And modern compilers always change the work schedule, especially when you turn on high optimization levels. So it shouldn't be a surprise that when I turn on high optimization levels, I end up with security vulnerabilities in my code often. Just reality. I'm sure you don't, but I do. All right, it's Wednesday, so we're going to have homework. Super tough homework this time. Here is some stuff. I believe I've got the hex file up on iLearn. I will check that again at the end of this class to be sure that it's up there. But if not, here it is. This is just a bunch of hex bytes. This is an offset at the colon, and then there are 16 bytes. So this is okay. This is offset 0. That's hex 10, which is 16. Hex 20 is 32, 48, and these are the bytes. So what is this? And what does it do? And how could you figure it out? Well, I'll give you a strong hint. Be sure you get your Linux environment up and available, and then go and read about this command right here, xxd. So xxd is a command line tool you should know about. Super useful. You get that file and figure out how to turn that file into an executable and run it. That's right. Take this guy, turn this into an executable, and then run the random bytes I've given you on your system. What could possibly go wrong? I promise this is not malicious. Okay. Save the output and only the output in start.txt, and then upload it as your answer. Don't embellish it. Just pipe the output to start.txt and then upload that. Okay. And once you've done all that, once you've figured out what xxd does, how it's relevant to this, and how you can turn this into an executable and run it, just for fun, run objdump on it. So you saw earlier that I can say objdump -d disassemble something, run it and see what's in the file. I think that's interesting. Are there questions about the homework? I will take silence as an indication that you all didn't get the mute button off fast enough, and move on. Next time, we're really going to get into assembly. So we're going to start a series of classes that's going to be a whirlwind tour of assembly. There's some optional reading. If you happen to have the book Practical Binary Analysis, read Appendix A. If you don't have it, that's fine. We're going to cover everything that's in there. I think some people just sort of absorb it better if they get to sit down and read it. We're going to cover a lot more information and in a little bit different way than what's in the book. So the lecture and the book should sort of supplement each other. But we're really going to get into assembly in earnest in the next class and walk through that.